All right, so for this video, this will be our second rotational dynamics video, and we're going to talk about moment of inertia. And so before we get to moment of inertia and what that means, let's remind ourselves of something in linear dynamics, which is the force, the net force, is equal to the mass times the acceleration. And if we solve for acceleration, we could get F net over mass. And so inertia really is a measure of how difficult it is to get something to change its state of motion, meaning how difficult is it to get something to accelerate. We'll take a look at this equation. Pretend you give it a constant net force. You can see that as you increase that mass, you decrease the acceleration. And so when it comes to linear dynamics, the measure of the inertia is really mass. That's how you're measuring how difficult it is to get something to accelerate. That's what its mass is. That's what its mass tells you. But things get a little more complicated in a rotation, in rotations, I should say. It's still called inertia. We represent it with an I now, though. And what we basically do is, well, let me give you an example first, because this is a really common example that we were doing in the class, and it's, as far as I know, most AP teachers do this example. But let's say we want to have a sword fight, okay? And we're going to fight with real swords. We're going to fight with little rulers, little meter sticks or something to represent our sword. And so along with this meter stick right here, we're going to attach a mass. And the question is this: do we attach the mass? Where do we attach the mass so that we can rotate or we can whap our classmates so we can get the greatest amount of rotation out of that hit? We don't want to position it so that we hurt the other student. We want to position it so that we can just rotate it very fast. And so the question is, well, would you put that mass up here at the top, or would you put it right down here at the bottom where you're gripping it? Well, if you put it at the top, it will hurt more. That's absolutely true. But it's much harder to get to rotate, right? It's going to rotate much slower the farther out from this pivot point or this axis of rotation that you have this mass. And so as it turns out, the closer you put that mass to where you're gripping it or to where it rotates, the less inertia you have, or the less resistance you have to how it rotates. And so we have a way of expressing it. So no longer, so just to be clear, you would be the same amount of mass either positioned here or here, but we can see the closer it is to the axis of rotation, the less inertia it will have. And so we have a basic equation that tells us about this. And I'm going to write this, but this is a general form. And I will say this, is that I'm going to give you guys a couple of examples. There's some examples in your on your homework or your assignment that you'll probably have to look up about what its moment of inertia is. You're not expected to memorize it. AP will never expect you to memorize this. What they will do is they will either give you the moment of inertia, or they'll tell you what the equation is for a moment of inertia. And so that it's important to know what to do with it. And so I'll give you two examples and show you how you deal with that. And then I'll do some more complicated ones in another video. But the equation for it is, it says that you sum, meaning you use that sigma there, you sum up all the individual masses. So I'll put MI to represent those individual masses. Pretend you have, in this case, you only have one, so it's easy, but pretend you have one here, So you add them all up, and then you multiply them by the radius squared. So the distance from this axis of rotation that they're at. So this is the general formula. This is what you would use if you had to come up with some general moment of inertia for some object. But as it turns out, most objects fall into it, one of a number of things that you'll be given. And so it's not necessary to memorize it. And so what are these general things that you'll see kind of often in rotational dynamics? Well, one thing that you'll see often is a disk, a cylinder or a disk. So I'm going to draw it like this. Pretend like this, you're looking head on to that cylinder or disk. And so it'd be rotating. I'll put the rotation, or the middle right there. It'd be rotating like this, or maybe like this. But either way, it's a disk. And the disk has a mass of m, and it has a radius of r. So one common example that you might see is, say, pretend you had an Atwood machine. So our favorite thing, Atwood machines. Pretend you have an Atwood machine like this, and you want to know, you want to say, you want to know what the torque is on it, or maybe you want to know what its angular acceleration, something like that. In which case you'd have to know the moment of inertia. And so how would you figure that out? Well, in this case, a disk is something so common that I'll just write the formula on here. And again, if you weren't given that formula, or I should say you would be given that formula, because AP won't make you memorize this formula I'm about ready to write down. They would either tell you what the moment of inertia is, or they would tell you what the formula is to calculate it. And so in the case of a disk, our moment of inertia, I, is equal to 1/2 mass of the disk times the radius squared, like that. And again, for the problems that I put on the assignment, you'll have to look up what is the moment of inertia specifically for that object. Another common one, might be a thin rod, in which case a thin rod, so actually I have to look this up because I don't know. But a thin rod, it depends on where the axis of rotation is. So for instance, a thin rod, a thin rod like this, if its axis of rotation is right down the middle, it's going to have a moment of inertia of 1/12 over L squared. So if this is the length right here, if this is L, that would represent L. Its moment of inertia would be 1/12 mL squared. And if you were to put the axis of rotation then all the way over here on the left-hand side, its moment of inertia then would be 1/3 mL squared. So again, you don't have to memorize these formulas. I'm just writing a couple just as examples. If you see any assignments that require you to calculate a moment of inertia, you just have to look up, say, what the moment of inertia of a rod is, or a disk, or something like that. So that is what moment of inertia is. And so how do we relate moment of inertia to Newton's second law like we did? So if Newton's second law is F net is equal to mass times acceleration, we could say that the equivalent for that is torque, so that's tau, I'll put net, is equal to the moment of inertia, because that's what takes the place of our mass now, that's what we call the moment of inertia, times that angular variable for acceleration, alpha. And so you can see that these two equations right here, when we start getting into static equilibrium, we're going to make use of both of those equations quite often. But the important part is this, is that now instead of mass, we have something called the moment of inertia, which tells us about how difficult it is to get something to rotate. And instead of force, we have torque. But that is what a moment of inertia is.